Okay, this is activity number two in problem num in and problem activity number two and lab number three. So we have a structure like that, which is made out of steel with default properties in Catia, and these top faces are clamped. The top faces of these little protrusions are clamped, and a total load of 500 pounds is applied on these four side edges, for these edges. So you're asked to use as many planes of symmetry as possible. And if you look at this, in all likelihood, most people are going to say, well, 1/4 of this is going to do the job. If you take 1/4 of that, it's symmetric all the way around, and therefore that's all you need to model. But when you think about it, actually there is a plane of symmetry because this is a square, because this is a square's profile. There is a plane of symmetry in the diagonal direction. So we have two ways of doing this problem. You can actually go ahead and create 1/8 of this geometry, or I can create 1/4 of it and then use a plane tilted at 45 degrees to cut it. And that's what I'm going to do. Okay. So let's go ahead here. Start with the start with the part file, and immediately I'm going to save this thing. File, save management, save as. I am in the folder. I've got to go to activity 2, lab 3, and I'm going to change it with this name. Good. I'm going to save it with this name. Okay, let's make it. On this horizontal plane, we will sketch. So it looks like I have something like this. We're going to clean it up in just a minute. Okay, let's dimension this. First of all, these side edges, these are 5 millimeter, 5 inches each. So this is 5, and this is 5, 5. All right, and this is 2.5. Based on the dimensions that are given you in the figure, you can check it out. This is 2.5. Okay, and yep, exit, exit, padded by 2 inches, padded up by 2 inches. And on this face, I will sketch that little circle there, and we're gonna clean it up. A circle. For now, I'm gonna draw it like that. The diameter of that circle is 1. Your total diameter is 1. And this circle is from this point to that point, it's 1.5. And from this point to this point, to this line, oops, let's try it. From the center to this line is also 1.5. Exit, pad it by 2 inches. Yep. Okay. Now, what I want to do is I want to cut this. I want to cut this with a plane at 45 degrees. So let me make a plane first of all, which is at 45 degrees, and the different ways of doing it. Please, you're not bound to do it the way I am, but anyway, here's a plane. We can do it by 3 points, for example. Where is it? 3 points. Let's see. 3 points. I want a plane through that point and and this point or the other one, it doesn't matter. So it does create a plane. You can see that it did create a plane, which is exactly at the orientation that I want. And now I use the split. Where is that saw? we're looking for the saw, and the saw, I believe, is in this surface-based feature. See, saw right there. If not, just go and look for a surface-based feature and select this. It doesn't matter which side we pick. We pick this side or the other side, so it's going to cut it like that. Actually, I would have liked the other side. No problem. Okay, flip it. Okay, good. Because I'm too lazy to rotate. All right, so we're going to make this thing out of steel with default material properties. So let's go ahead and just make sure everything is okay. So what we did, we created only 1/8 of this. Okay, good. So metal, click on the material, apply material. Metal, steel is down here on that part. Remember, for me, if I double click on this, my software is gonna on this computer is gonna crash. But for you, you can double click on this thing, go and change the appropriate Poisson ratio, Young's modulus, coefficient of thermal expansion, and whatever I want. Now, these things don't happen to me in class because over there I use my other laptop, and on other laptop, the software is working properly, and I can change that. So whatever I demonstrated for you in class, actually, there was no issue with it. But here, save everything. Good. So now we're going to go to analysis and simulation for analysis and simulation, generative structure analysis. Catia uses default static, which is good. That's what you want, and it measures it based on the sizes that you sees. So let me see what kind of size do you have here. A parabolic element. I mean, if you can make this thing smaller. So remember, these things are critical. However, we are not spending too much time on it right now. If you want to look at the mesh, put the cursor on the nodes and element, right click mesh visualization, and it looks like that. Okay, so yeah, looks like that. Okay, deactivate the mesh. Okay, good. Let me save the analysis file. File, save management. Part was saved, but the analysis is not. Save as, and I'm going to say go to one level up to the right folder, activity 2, and I'm going to say problem 2. How about that? Please make sure you master these things so that you don't overwrite things on a test and final exam. That's why I'm giving them different names so that I can recognize them. All right, the top is clamp, clamped icon, surface slider, and other stuff, and user defined. Don't worry about this last guy. On purpose, I want to talk about it right now. Now, this is a plane symmetry. So put a surface slider here. See that? Surface slider, the first one. See? Click there. And this is a plane symmetry. This side and that side are plane symmetry. And what are we doing? We are applying a force of 50 on this edge because it was 400 on all four edges. This is half of one of those edges. So I'm going to apply force on that face in the direction Z. Direction Z. Now remember, these are Newton. If it's bothering me, I can go and change these units to pounds. I can do it right now, but let me not do that. Go to tools, options, parameters and units. Let me find the force and change it to pounds. Now, uh, you can click on magnitude so that it puts it in the alphabetical order and find the force that way. Force right there instead of Newton. I'm going to go to pound. I could have typed uh, uh, 50 pounds there, lbf, but I decided not to. Clicked on it, go to pounds. So I don't have to worry about watching things anymore. So force on that edge, notice that it says LBF, so negative 50 pounds. Click on the save, click on the calculator. Actually, this says compute, doesn't say calculator. Click on it. Ignore that message. In the newer versions, you don't get that message. And say yes, run it. No issues. You want to look at deflection? There we are. That makes sense. These faces remain flat because there are surface sliders on it. And of course, you're pushing this thing down. You can look at numbers if you want. You can animate it. Here's the strip of film. Animate. That's the way it should be, right? You should go down. When you apply this edge, apply force on that edge, it's going to go down. If you want numbers, you click on the displacement and notice that every node will go down. Okay, double click on it, select the average ISO under the visualization tab, select the average ISO, and there we are. And this is a very tiny amount because it's a very bulky piece. 50 pounds is nothing. If you want to look at the von Mises stress, you click on it, and you're going to get roughly, I mean, these places where you don't have fillets, you have big stresses. Now, the reason actually you have big stresses there is not only the fact that there is no fillet, but because you're applying a force, edge force. Edge force is just putting a knife there and trying to push it down. Okay, so you've got to be careful. Now, if you want to look at the stress distribution elsewhere, not close to these, because these can be, you have to be very careful. There's no way you can apply edge load, but let's pretend that we can. So let me deactivate this plot, deactivated that, and look at the stresses in this area. So let's make a group, and there are different ways of making group. I talked about it in the first tutorial. There we are. Except that I want to move this thing. It's not in the right spot. So let me try to move it for you. First of all, I can take this and move it there and resize it as I see fit. It took the last one that I had from the previous example, move it further, and let me see. Yeah, and I mean, this is too big. I don't need it. It just makes me confused. Confuses me really good. I don't need that box that big. Okay, so, and you can, oh, oops, in the wrong spot. Aha, that's better. So we can look at the stresses in that area. In fact, if you want to go all the way down, you just go down like that. And you can hide the group. Look at the von Mises stress right here, activated. Double click, but select the box group right there. So it puts away all that junk here, which were caused because of the edge load and also because of the lack of fillet there, and it shows you the one Mises stress distribution through this. Okay, uh, yeah. I mean, they're very low. This is steel. Basically, that's nothing. But it with the other ones being there, those unrealistic ones, or perhaps bad ones because of the way you modeled a load as an edge load or concentrated force, it masks the stress distribution here. That's why this all look blue. If I double click on this and say show me everything, notice that the place, where's my group? Let me show you group. I then show those colors were in this area, but we cannot see it because these are gigantic stresses that are not realistic. So save it, and this takes care of the second problem.